In this presentation, we will implement the full adder by using only the NAND gate. You already know that the sum in case of full adder is given as A XOR B XOR Ci, where Ci is the input carry, and the output carry Co is given as A and B or Ci A XOR B. This is something we have discussed already in the full adder explanation. Now you might be knowing that the XOR operation or your XOR gate is implemented by using the 4 NAND gate. This is we discussed in the half adder implementation of the NAND gate, and also while we were discussing the universal gates. So let's move to the sum first, then we will see what is the carry output. Here we are having the 3 inputs to the sum to our XOR gate A, B and Ci. So you may have a 3 input XOR gate, or you may have a 2 input 2 XOR gates. So we are implementing it with the NAND gate. So first I will make first XOR gate in which the inputs are A, B. Then I will make the next XOR gate in which the one of the input is Ci and one of the input is what? The output of your first XOR gate. It's very simple. What I'm actually telling you is that we require one XOR gate, and in which the inputs are A, B, then whatever its output we will give it to the another XOR gate, and this is your Ci. So the output will be what? Your sum, which is equal to A XOR B XOR Ci. Very simple. So we will try to make this XOR gate by using the NAND gate. So let's do it. We require 4 NAND gate for the XOR implementation. So let's make it. This is our first NAND gate, this is our second NAND gate, this is our third NAND gate, and this is our fourth NAND gate. Now watch it clearly that how we implement it. This is our first input, let's say A. This is our second input B, and the A will go to this gate also, and B will act as one of the input to this gate. Now the output of this gate will go to the input to this one and also as one of the input to this one. Then the output of both these gates, this one and this one, will act as the inputs to this last NAND gate. So at this point, what we are having at this point, we are having A XOR B. If you want the proof of this thing, then I have did it in the half adder implementation and also in the universal gate. So move to that lecture, you will find the answer of your questions. So this is, we got our A XOR B. Now we want the XOR operation with Ci. So it's very simple. We are going to make this arrangement again. So let me copy it down. Let's copy this part, copy and then paste, and let's put it here. Okay, fine. And this input is our Ci. In this case, the output here will give you A XOR B XOR Ci, and this is what? This is our sum. Now we have implemented the sum. This is time to implement the carry output. So carry output requires A and B, and it requires Ci and A XOR B. So it's very simple and a little bit tricky. So let's see how to do that. At this point we are having A and B and then its whole complement. Fine. And at this point we are having what? A XOR B and Ci and then the complement of whole. Very fine. Now we want the OR operation between A and B and Ci A XOR B. So what we do? I will take this point and this point and then simply pass it to another NAND gate. Okay, this point and this point will go to the NAND gate, and let's see what is the change in the output. So the output will be what? A and B, then its complement. Okay, and then again it is ended with what? A XOR B, okay, and CI. Fine. Now there is a whole complement of this thing. So by using the De Morgan's law, I am having A and B. This AND will convert to what? The OR, and then CI A XOR B. There is a whole complement here actually, and this whole complement to this thing is gone because of the De Morgan's law, and this is similar to our C output. So this is how we implement the full adder by using the NAND gates only. So in the next presentation we will implement the full subtractor by using the NAND gate. So see you in the next one.